Everyone, thank you for the introduction. So to start, the research was possible thanks to the collaboration of Northampton University as well as the EES UK. And the research of the paper I'm going to show today is going to be speaking about the journey of development of the product itself. To start with, the collaboration was possible thanks to Innovate UK partnership or knowledge transfer partnership program. The program allows UK businesses to partner with educational institutions to innovate for growth. The objective of the KTP was to develop fireproof gate, a modular, compact and portable solution to blanket lift entrances while lift door is removed due to servicing or prior to the installation. The crucial aspect of the FPG was to achieve 2 hours fire rating and for it to be aligned with elevator code and fire door standards. Although the similar solutions are available on market, they are mainly either non-fire stopping or the non-fire resistant, or they achieve the fire resistance through intermittent coating. Normally, there are limits to the actual use of that kind of solution, and also the length of the fire rating is shortened. At the beginning of the project, we looked at various standards relating to industry, and from our finding and the results of those findings, we narrowed down standards to the applicable to the actual application, the one listed on the screen here. From the beginning, the team discovered that the FPG, the fireproof gate, will fall in between of the landing door and fire safety of the regular fire door. Due to its use, it's never going to be used in fully operational lift, but at the same time has to provide the fireproof capability of the fire door in that scenario. We started off by developing the concepts, so the construction as well as mechanical functionality was developed, was modeled in engineering software. That was mainly SolidWorks, and material which will be used for the build of the fire gate was investigated. We've narrowed down to composite materials with specific emphasis on the fire of the fiberglass for its fireproof capabilities, and that was thanks to the development of the material in recent years. As you can see, that was the motion study of the actual gate, the first of our approaches. Developed concepts were first modeled, as I've mentioned, in engineering software, which was SolidWorks, and FEA tested in the simulation software for its sufficient strength and durability. The results of the simulation were ultimately validated with experiment testing. And this, the test shown actually over here is of the pendulum test. It's very close or similar in principle to the test specified the EN8150, where the 45 kilo weight is dropped from the height of 0.8 meter, and it hits the door or door set in that case at height of 1 meter. And if you can see here, the structure was rigid enough, strong enough to actually withstand that force. We were allowed to get deflection or permanent deflection of 0.12 of a meter, which we very clearly satisfied there. Simultaneously, we worked in collaboration with University Institute for Creative Leather Technologies laboratory, where we're allowed to use the small scale furnace. This gave us opportunity to test various materials and different components, obviously on a smaller scale, but luckily the furnace was able to achieve temperatures exceeding 1100 degrees, which gave us a lot of information. We were able to eliminate a lot of materials and prepare better for the final and full-scale test. Final prototype was then tested in BRE Certification Center in Watford. It actually achieved a 4-hour integrity rating and 1 hour radiation fire rating. So for those of you who are familiar, the integrity is actually the components of the fire gate is in place and intact with a certain criterion that has to be met with the gaps and possible, and then also the W, which is radiation, which is a partial insulation against the temperature and the high energy flowing through the gate itself. The test, although not the first time, was actually we achieved the results with exceeding our first set out goals. And it is worth mentioning the performed test was done according to the fire door set testing, which is EN 1634. And all the performance criteria were measured accordingly to that standards. As you can see here from the video, this is the fire gate at 4 hours after the test. We actually have done the overrun, so that means that we've added 20 minutes over the 4 hours. That give us ability to actually extend or the change dimension. So we can add 15% in each direction of the gate in case we want to adjust it to a different applications. So to conclude, the KTP research has proven that the development of a certified fireproof gate is possible. The product is lightweight, strong, and durable, thanks to composite material and steel frame. The plan for the future is to further investigate the composite materials and develop different mounting mechanisms as well as sizes variation to meet industry needs. And this will include the further weight reduction, insulation properties, and smoke stopping capability of the gate itself. And also, as the project formed the basis of my doctoral degree thesis, I intend to develop the CFD model of the FPG. Once the model is validated against the experimental data, it can be used to analyze the viability of using FPG in various use scenarios. And one of the examples of those scenarios will be counteracting the stack effect. So just briefly to elaborate on my last point about the stack effect, for those of you who are familiar with, it's a phenomenon which occur in a high, or for example, it's a staircase shaft, or in this case is a lift shaft. And this phenomenon was one of the reasons the actual research was instigated. It was one of the reasons we wanted to work on the project itself. So as illustrated in figures, the movement of air inside the shaft, or as it is in the last case of the figure, is actually the chimney of the building, is due to the air temperature differences. So obviously the hot air rises. While it rises, actually creates negative pressure, or the variation of the pressure in relation to the neutral pressure inside the shaft, which actually caused the spread of fire. In many cases, the fire across the floor, so it can transfer from the lower floor to the higher floor, and also in some cases sucks in the cold and fresh air from surrounding area into the fire room, which is very dangerous, especially in case of fire in tall buildings. Therefore, the FPG can greatly improve fire safety and prevent excessive damage to engulfed building in which it is installed. Now, just to finish off, the FPG has been successfully built, and we are in the process of bringing it into high volumes production. Its patents are pending, and the production official launch is planned for the beginning of next year. You can see actually the sample of one of the prototypes is an earlier prototype on our stand of University of Northampton, and it's going to be distributed by the company EES UK, the one that I've mentioned in the beginning. Finally, I would like to use this opportunity to thank everyone involved in the project. That is the UN as well as EES team members, and very big thanks to Knowledge Transfer Advisor Kamran Hussain from KTP office Innovate UK for supporting us all the way through and actually make this research happen. Thank you very much.